Go ahead and start recording, and let's just work out this practice problem. So, right, we're going to start off with the square loop. It's going to have side lengths of 8 centimeters. Let's make that a little bit clearer. Okay, so we have a square root, 8 by 8 centimeters, and I'm giving you the resistance of 0.02 ohms, right? Side length 8 centimeters, R equals right, and it's going to be sitting inside a uniform magnetic field. Right, so it's here. Give it some colors. If it's pointing out of the page, that means that we're having which I'll call B external. Right. And now for the induction, right? What we're going to do is change the field strength. We'll do that over a course of 10 milliseconds. And this will then induce a clockwise current. Of 150 milliamps. All right, so we're going to scroll a little bit and then start getting into problems. We're going to break this into 3 parts. All right, so part A. Is the external field getting stronger or weaker? Or weaker? Right. So let's draw the loop again. So what do we say? We said we're going to have this square loop. Some current gets induced. We said it's going clockwise, so I induce. And let's do our right-hand rules. The induced magnetic field by right-hand rules. Let's say I go for the top of the loop. Top of the loop, I'm going to see going that way. Measure inside the field. I see a loop. I see current going into the board. Right. So, come back up here. The external field was coming out. Our induced field here is going into the board. So they are opposite. Let's see here. The induced is opposite to the external. So the external field is increasing, right? Opposite flux means I'm going to have to reduce, go against it. the field strength is getting stronger. All right. Next part. Let's calculate the induced EMF. All right. So we're doing induction stuff. So naturally, let's assume that we can apply Faraday's law. So, right. We'll have the induced EMF is equal to magnitude, change in flux, change in time. All right. So far, so good. Our flux. Right. Remember our picture? I'll go back up. Our flux is nice and uniform. Right. Our flux is nice and uniform. Pointing out of the page, increasing. So the only thing that's changing about it is its magnitude, not the area. The loop isn't changing in size. So we're going to have E equals delta BA delta T, which we can reduce to just pull out the A. It's not changing. The area is not changing. Delta B delta T. All right. Now I'm going to say we're stuck. Right? For simple reasons. We don't know B or the induced field strength yet. Right? Don't have B or E. So we're going to need another equation. All right. The trick is that way back in the beginning, we said, hey, there's this square loop, and we give its resistance. So let's see. Come back up here. Right? I said how much current got induced in that thing, and we know its resistance. So we can just apply Ohm's law to get the EMF that's induced in this loop. We just say, hey, we know the current, we know the resistance, calculate the EMF by Ohm's law directly. So let's scroll back down. E equals I times R. Right. I, it was 150 milliamps, or 150 times 10 to the minus third amps. R was 0.2 ohms. All right, 150 times 2, that's going to get us to 300. There's 10 to the minus 3 here, and a 10 to the minus 1 there. So we're just going to say this is now 10 to the minus 4th volts. Or play the decimal places, 0.03 volts is induced. So, last part, we're going to wrap this up now. We asked earlier, hey, can we use Faraday's law to get the EMF? And the way this problem was written, no, but we can use Ohm's law to get that magnetic field strength. So we'll ask, what is the magnitude in change of field strength. So we'll bring back Faraday's law, all right? We'll use our previous work. We said E is equal to area, change in field, times change time. We know everything but the field strength. So we'll just manipulate the variables. We'll say this is now E delta T over A equals B. And I'll also make an explicit note here that I dropped the magnitude signs. Everything's going to be here, everything's going to be positive here. Right. And let's just plug things in and figure out how much the field strength changed. So E, 0.03 volts. Time change, we said it was 10 milliseconds at the very beginning. We said for 10 milliseconds, the field strength was changing. So we're going to call this 10 times 10 to the minus third seconds, all over 0.08 meters squared. Remember, we're dealing with a square loop here, so it's just the side length squared. Right. And won't use any calculators yet, so we can still play around with this. Right. Let's just isolate powers of 10. So it's 3 times 10 to the minus 2. That's 10, instead of 10 to the minus third, this is 1 10 to the minus 2. And this is 8 10 to the minus 2 squared. Don't forget the units on the end now, it's Tesla. All right, so we've got 3 divided by 8 squared times 10, just add up powers of 10. So let's see here. Minus 2, minus 4, minus 2 squared gets us another minus 4. So this is 10 to the 0th power. And that leaves us with 3 over, forgot the units, 3 over 64 Tesla. And you plug in your calculator, you'll find that's about 0.047 Tesla. Is the change in field strength. All right, so we'll call it into this practice problem there.